there we go. Alrighty. So we're continuing on with bone tissue. This is where we ended. So I stopped at talking about long bones. Basically, there are those different shapes of bones. The most detail I'll give you is on these long bones, which I already went over. I'm going to talk a little bit about the flat bones in just a second. So to give you a heads up of kind of where we're going, this chapter, bone tissue, has a lot of new terminology and kind of confusing terminology, and it can get sort of complicated. And most of it, we're not quite halfway through. We'll be well over halfway through by the end of today, but it's just a lot of lecturing. So me kind of talking. There's not a lot of opportunity for kind of other activities. So bear with me through this. It can get really confusing, but we're kind of setting this all up so we can start talking about the skeleton and learning the different bones. Not that this isn't important, but on Friday, we'll start getting into learning the 206 bones of the body. So until then, it's mostly lecture. Once we get into the skeleton, it'll be a little bit more interactive. But for now, it'll be me, like I said, talking a good bit. So try to pay attention as much as possible. It can get a little confusing. I tried to repeat a few really important aspects. You'll see some kind of repetitive slides in here. And I've sort of whittled it down again to what I think is the most important for an AMP1 class. So I've simplified it down compared to what's in the textbook. So if you've done the outline, you probably saw that it was a pretty complicated chapter. And I've, like I said, kind of simplified it down a little bit. If you haven't turned in your chapter 7 outline, definitely do that. You can still get credit for it. It'll just be a slight penalty for being late. And that was due today. Okay, I think that's all kind of the upfront stuff I wanted to talk about. So we're going to get back into bone tissue. We ended here talking about the epiphyseal plate. This is that part of the bone, the ends of your long bones. So say your femur. So this is the top of the femur that actually allows for growth and length over your lifetime. Well, until you're probably about your age, late teens, early 20s. Okay. So that was long bones. Next, we have flat bones. Flat bones, the most common area is going to be kind of your cranium, your skull is where flat bones are really prominent. And it's just a sandwich of compact bone on the outside, spongy bone on the inside. I'm going to talk about sort of the differences of compact and, well, I'll go into a little detail on the spongy bone in particular. I haven't talked a whole lot about that. But spongy bone looks like a sponge. It has all these spaces in it. It's not as hard. I'll talk about the importance of it in a little bit. The compact bone on the outside of all of the bones of your head, essentially, help protect the organ inside. That spongy bone basically helps absorb shock. So if you get hit in the head, the compact bone is going to keep whatever hit you in the head from actually hitting your brain. And that spongy internal piece is going to help your brain to not be, not basically hit up against your skull, right? So it allows for some shock absorption. So shock absorption plus protection is kind of the importance of these flat bones. And that's really all I'm going to talk about with the flat bones. There were also the short and the irregular shaped bones that I mentioned. I'm not really going to go into detail on their anatomy. I'll talk about them, you know, when we get back into the skeleton, but the long bones and the flat bones are the only two where I kind of going into detail here. Okay. All right, now getting into something that can get confusing pretty quickly, the histology of bone tissue. Here, I'm just going to talk about 4 different types of cells that basically make up bone tissue or part of the bone tissue. So I'll talk about the cells, and then I'll talk a little bit about the matrix that the cells are sitting in. And remember, the matrix is also called ground substance. It's sort of what the cells and the fibers are suspended in. If you think of a Jello mold, the Jello part is the matrix, and then the little bits and pieces of whatever you put in Jello molds are going to be the cells or the fibers. I'm not really going to talk about the fibers, really just the cells and then what the matrix is made up of. There are 4 types of bone cells, all of which sound really similar because they're all osteo something. Osteo obviously refers to bone. I'll go through each of these on the next 4 slides. You have osteogenic cells, osteoblasts, osteocytes, and osteoclasts. So you can see how this is going to get confusing pretty quickly. I'll talk about what each of them does. They all have a slightly different function. So I'll talk about those on the next few slides. There's kind of a breakdown, a very simple outline of what each of these cells does here for you to kind of refer back to. Okay, so I'm going to go into each of these. The first one, the osteogenic cell, is a stem cell. So you guys have probably heard the term stem cells before. These are just cells that give rise to many other kinds of cells. In this case, it's cells that give rise to other bone cells. They are found specifically in the endosteum, which, if you remember, again, lots of terminology, I know. The endosteum is the lining of the marrow cavity. So if you think about the cavity in the middle of your long bones, it's lined by what's called the endosteum. So they're found in the endosteum, and then the inner layer of another lining, the periosteum, which is the sheath around the outside of your bone. So those are the 2 places that osteogenic cells are found. An easy way to remember, well, maybe this is how I think of it. Osteogenic, they generate bone cells. So they make new bone cells, essentially. And that's all the detail you really need to know about osteogenic cells. They're giving rise to other bone cell types. Not all of them. One cell type is formed separately. All right. So the second type of bone cell is called an osteoblast. These are the cells that essentially form the bone. They can't divide themselves, so they're non-mitotic, but they come from osteogenic cells. So those osteogenic cells that I just talked about, the stem cells, basically turn into osteoblasts. The osteoblasts then are going to secrete the matrix around them. So the bone, the matrix of the connective tissue. So they're really forming the bone. That matrix then solidifies or calcifies, and they get trapped in there. So they're synthesizing and secreting this matrix around them. It hardens, and then they get trapped in these little cavities. When the osteoblasts get trapped, they're no longer secreting bone matrix, and they become osteocytes. So osteoblasts become osteocytes. That's the trajectory. Osteocytes are mature bone cells. I'll go into them in just a minute. So it's kind of weird that these cells are secreting something that they then get trapped in. It's a little bit strange to think about. And you've probably heard that, you know, exercise, weightlifting, all that kind of stuff is really good for your bones, which you wouldn't normally think. You think it's good for your muscles, but physical stress on your bones, which your muscles place physical stress on your bones every time you use your muscles, that actually helps to build your bone mass. So it creates more bone tissue essentially. So when you have that physical stress, what's happening is these osteogenic cells are multiplying really quickly, turning into osteoblasts. Those osteoblasts are then secreting a whole lot of bone matrix. So it actually reinforces your bone. So if you've heard of ways to limit or avoid osteoporosis, it's really important to actually, along with nutrition obviously, but actually stress your bones to a certain extent, to a healthy extent. But you want to put stress on your bones, whether it's walking, weightlifting, running, whatever, any kind of exercise that makes your muscles work harder and put stress on your bones is going to be healthier for your bones in the long term because of this whole process. It makes more osteoblasts, which makes more bone matrix. Okay, so those are osteoblasts. An osteoblast always becomes an osteocyte. That always happens. So next we're going to go into osteocytes. They're former osteoblasts. They've gotten trapped. They can't move anywhere. They're in this hardened calcified matrix that they previously secreted when they were the immature osteoblasts. So here you can see an osteocyte, and then that kind of white area is called, it's the space that the cell is trapped in, it's called the lacuna. So here you see the word lacuna. So you guys on Zoom, this white area is the lacuna, this kind of grayish blob is the osteocyte. This is what's found in mature bone. So once your bone has hardened and become what we think of as bone, these are the cells that are there. They're not secreting any more matrix. All they're doing is balancing the minerals within that matrix. So a lot of calcium and phosphate, basically. They're kind of keeping that balance. They're not making more bone, they're just helping that mineral balance in the bone. Lacunae, so lacunae is just the plural of lacuna. This is where the osteocytes are trapped, kind of by their own making. And they can actually communicate with each other, even though they're not in direct contact with each other. So these osteocytes can communicate through what are called canaliculi, which are just little connections between the lacunae, between those cavities where the cells are trapped. They can communicate between there via electrical or chemical signals. You can't really see them on here all that well, but they're connecting these little black dots, which are the lacunae. So for you guys, these are the lacunae, and then the canaliculi are these tiny lines basically running between the lacunae. All right. So osteogenic cells to osteoblasts to osteocytes. It's sort of the trajectory, which I think I have here. Yeah. Stem cell is going to form the osteoblast. The osteoblast secretes the matrix hardens, traps the osteoblast, and it becomes an osteocyte. So that covers 3 of the 4 cell types I mentioned on that first slide. And last but not least, we have the osteoclasts. These are, I don't know, these are my favorite. If you can have a favorite bone cell, I guess this is my favorite bone cell. These actually dissolve bone, which is sort of strange to think about, that our bones are dissolving themselves. They're growing and dissolving throughout your life. So osteoclasts are what is actually dissolving kind of old or damaged bone tissue. They're cells, they're really big cells. They have up to 50 nuclei, so they're huge cells. And they basically go around eating bone tissue. They're sort of weirdly shaped, as you can see here. So here's the multiple nuclei. They have this ruffled border, which just increases surface area. So if you remember anything about surface area, the more surface area there is, basically the more bone they can dissolve. So they secrete and create an acidic environment that dissolves the bone, and then they kind of ingest it more or less. So that ruffled border increases surface area, which allows for more efficient dissolution of the bone. Oh, I forgot to mention, osteoclasts don't come from the osteogenic cells. So osteogenic cells create those osteoblasts. Osteoclasts, it's really confusing, actually come from bone marrow cells. I'll talk more about bone marrow, but just a different origin, essentially. So they don't come from the same place as the other bone forming cells. All right, so those are the 4 cell types. They're easy to get confused, but I think if you kind of sit down, just remember that trajectory of the first 3, osteogenic to osteoblast to osteocyte, and then know that these osteoclasts are kind of totally different. Hopefully that'll make sense, and that's really all the detail you need to know about those 4 cells from my perspective. Here's an image sort of how these osteoclasts form. So you have these stem cells. These are bone marrow stem cells, so not the osteogenic cells. So different stem cells, they actually all fuse together. So that's why there's multiple nuclei in one eventual osteoclast. So you have all these stem cells fusing together, forming this really weirdly shaped cell that then basically docks into a bone and then will absorb some bone tissue. I'll show you an animation of sort of what that looks like towards the end of class. Okay, so those are, yeah, that's all the bone cell stuff I have. Now I want to talk really quickly about the bone matrix. So like I said, you have the matrix, which is kind of the jello of the jello mold, and then the cells are dotted within there. So we talked about the cells kind of suspended in the matrix. The matrix is really important in providing both strength and flexibility to the bones. So the matrix that the bone cells are secreting, essentially. There's an inorganic or ceramic portion of the bones. This is the really hard part of the matrix. It's made of something called, primarily of something called hydroxyapatite. Don't worry about the molecular formula of that or anything, just hydroxyapatite is the hard ceramic solid portion of the bone matrix. That is essentially what allows for the structure and support of the skeletal system. I think there's a group in here doing rickets, which is actually a bone disease caused by mineral deficiency. So that results in soft, deformed bones. I'm not going to go into a whole lot more detail because I don't want to overstep and say too much because you guys are going to be watching each other's videos. So you'll learn more about rickets then. But rickets is where that matrix, the hydroxyapatite, basically doesn't form correctly, and you have really soft pieces of bones. All right, so you have that portion, the hard portion, the ceramic portion, and then you have the polymer portion as well. So it's this composite material of really hard and kind of flexible material. The flexible side, we know bones are hard. That makes sense that we would have a ceramic portion. The flexibility comes into play because your bones actually need a little bit of give in them. Otherwise, they break really easily. So a little bit of flexibility in your bones is critical. And that's done through collagen fibers. So the polymer or the organic portion of the matrix is made up of collagen fibers, which are those protein fibers that I mentioned a while ago. I don't think anyone's doing brittle bone disease in here, but brittle bone disease is basically where those collagen fibers are not deposited correctly. So there's really no flexibility in an individual's bones and they break very easily. All right, I think that's all I have about the bone matrix. So there are kind of two pieces to that bone matrix. All right, this is a little bit out of order. I don't know why I put these slides here, but this will be kind of repetitive or stuff you've heard before already. So going into a little detail about compact bone, then I'll talk a little bit more about spongy bone. Hopefully most of these terms you've heard before and are sort of a review from lab or earlier in this lecture, or I guess the histology chapter maybe. So bone tissue, specifically compact bone, is made up of these repeating units called osteons. So an osteon is essentially a central canal surrounded by these concentric circles. So one of those is an osteon. An osteon is sort of defined by the central or the Haversian canal. And then around it are where the bone cells, the osteocytes, are found. So in these lacuna, these little dots, that's where the bone cells are once they've gotten trapped in the matrix. I already mentioned canaliculi, so yeah, sorry, it's a little repetitive. Canaliculi are connecting those little lacuna where the bone cells are so they can communicate. All right. Spongy bone. I haven't talked much about spongy bone. I kind of just showed you some images. It looks like a sponge, obviously. That's why it's called spongy bone. It's actually fairly strong, so it has kind of the benefit of being strong with minimal weight. So it lightens your skeleton a little bit, but still provides support and shock absorption. It consists of essentially a lattice structure of bone. The bone is covered with endosteum. Remember, that's what's lining the marrow cavity of long bones. So it's a specific type of lining that's lining all of these pieces of bone. Those plates, the thin plates of bone, are called trabeculae. So all of these plates that you see here are specific, they have a specific name. It's trabeculae. So there, that would be trabecula. The spaces in between all of those are filled with red bone marrow. I haven't talked about bone marrow really in detail. I think on the next 2 slides, I'll go into some detail on bone marrow. But bone marrow is filling all of those holes. And I'll say why bone marrow is important in just a second. So you have this lattice of bone filled with bone marrow, specifically red bone marrow. There's 2 types. All right, so that's spongy bone. Into bone marrow. Good. Thought this was next. Okay, what is bone marrow? Everyone's probably heard that term. You've heard bone marrow transplant, something like that. So bone marrow is just a very soft tissue, essentially occupying the marrow cavities of long bones. So I showed you that on Friday. So in the middle of your long bones, which are like your limbs, arms and legs, you have a cavity filled with marrow. And then also in the, like I just said, those spaces, the holes in the spongy bone. So what is so important about bone marrow? Well, there's 2 types, first of all. There's red and yellow. So red marrow is what's found in the spaces of the spongy bone. It is very important because it produces your blood cells. Red blood cells, white blood cells, and platelets, which help with clotting if you ever get a cut. So all of your blood cells are produced in this by this red bone marrow. In children, this is found in pretty much every bone because children are growing really fast, so they need kind of constant new influxes of blood as their body grows. Once we get to adulthood, it's found in kind of specific areas, sort of in the central part, like the trunk of your body. When we get into the skeleton, this is the axial part of the skeleton. So axial is kind of your head down into your trunk and pelvis area. So it's found in the skull, the vertebrae, your spine, ribs, sternum, parts of your pelvis, so your hip bones, and then where your arms and legs essentially connect. So the heads of your humeruses, and your femurs. That's the only place that red marrow it's a lot. That's where red marrow is found after childhood. And that's mostly because that's where our flat bones are. So ribs are flat bones, skull, most of your cranial bones are flat bones, and those have a lot of spongy bone in between. And remember, the red marrow is found in those spaces in the spongy bone. Okay, so that's red bone marrow. What about the other kind? Yellow marrow is found in the long bones. So your arm bones, your leg bones, essentially. It's really just it's mostly adipose tissue. So it's fatty and holds on to a lot of energy. So it's a great energy reserve. It does not produce blood cells, typically. Well, yellow marrow never produces blood cells, I should say. In extreme circumstances of anemia, so if you're anemic, you don't have enough red blood cells to carry oxygen around your body, which can make you really tired and lethargic and kind of feel overall not so great. So with anemia, fewer red blood cells means less oxygen to parts of your body. So in extreme cases of anemia, the yellow bone marrow will actually turn back into red, and then it'll start producing blood cells, which is pretty crazy. So it can change back into red marrow when there's kind of long-term anemia, a long time period where you don't have enough blood cells to sustain yourself. Not really a situation you want to be in, obviously, but it's kind of a nice response of our bodies in case we need more blood cells to be produced. Okay, so that's bone marrow. There's a lot more to know about bone marrow, but for now, it's really all you need to know. Okay, now we're going to get into an often confusing topic, how bones develop. Mostly I'm talking about this from the perspective of initial development of bone. After this, I'll go into how bones actually kind of remodel themselves. So I don't know if you knew this, but every 10 years, essentially, you have a whole new skeleton. So all of your bone tissue has replaced itself every decade. That's bone remodeling. Right now, I'm going to talk about that initial, when you were in utero, growing as a fetus, what happened and how your bones developed from there. So the process of bone development is called ossification or osteogenesis. In the fetal stage, humans are primarily just cartilage. So it's a cartilage skeleton in utero, and it'll eventually become bone. I'll talk about how that works. Yeah, by birth, most of the cartilage has been replaced by bone. Some of it will remain and be replaced by bone throughout childhood. And then we still have some cartilage, obviously, in our ears and our nose that never gets replaced by bone. There's two methods of bone development. They're both long words that I don't have a whole lot of a great way to remember what they are. But you have intramembranous and endochondral ossification. I'm going to talk about each of these. If you did the chapter 7 outline and you kind of looked into these in detail, you'll realize they're sort of complicated. So I have boiled them down to essentially 2 slides and pulled out, I think, the most important pieces for understanding how bones develop in these 2 ways. Different bones in your body are formed by intramembranous versus endochondral ossification. So it's happening when you were still developing. Intramembranous and endochondral ossification was happening at the same time, but it's just a slightly different process. So I'm going to talk about each of them, and hopefully my simplification doesn't just make it more confusing. But like I said, I've kind of boiled it down to what I think is sort of most important. All right, first, the intramembranous ossification. This is where connective tissue is turning into bone. So connective tissue that's basically not cartilage, it's turning into bone. Or I guess some could be cartilage. I'll talk about how that's different from the endochondral in just a second, but this is happening in a very specific area of a fetus's growing body, basically from the collarbone up. So collarbone, jaw, and cranial bones are formed by this process. Those are the 3 areas specifically that are formed by this very specific type of bone development. Everything else in fetal development is essentially the other one, endochondral ossification. This process also occurs throughout your life as your bones strengthen and remodel. So as you kind of rebuild your whole skeleton, this is what's happening, the intramembranous ossification. So connective tissue turning into bone. I boiled it down to 3 essential steps, and most of these, this should kind of make sense based on what I talked about already with the bone cell types. So first you have the osteoblasts, which are those cells that secrete the matrix, right? So they are essentially in the connective tissue that's there before the bone. So if you imagine your skull, there's connective tissue there. Before there's bone, osteoblasts develop there and then start to create that bone tissue. So before it's not bone tissue, osteoblasts secrete the matrix, which then calcifies and hardens. That becomes bone. So that's the first and main step in this process. And then you already know this, osteoblasts are going to become osteocytes because that matrix is going to harden around them and trap them. They then become osteocytes. That'll form essentially the spongy bone specifically and the periosteum. The periosteum is the lining around the bone. And then this is where I cut out a good bit of detail. And then the compact bone forms. So there's more that goes into that obviously, but this process, I think this is a good basic outline for what you guys need to know for the process of intramembranous ossification. So first the spongy bone forms basically, and then around that the compact bone forms. And then you have bone where there was once just connective tissue. Okay. So that's the one way that bone can form. And remember, that's the skull, collarbone, and jawbone specifically. And then endochondral ossification is where that initial cartilage skeleton of the fetus, so it's kind of like a blueprint, eventually is replaced by bone tissue. So it sounds really similar. Intramembranous ossification technically is connective tissue becoming, like another connective tissue, becoming bone tissue. Here, cartilage doesn't become bone tissue, it's just replaced by it. I know that's a really minor difference, but that's essentially, from a developmental standpoint, that's the difference. It's either replaced by or turns into. Connective tissue turns into bone tissue, which is intramembranous, or it's replaced by bone tissue, which is endochondral. It's a fine line. So this is going to form most of the rest of the bones of the body: the vertebrae, ribs, limbs, pelvis, scapula, sort of everything beyond the cranium, jaw, and then collarbone. So the vast majority of the fetal skeleton develops through endochondral ossification. It doesn't actually start until the 6th week of fetal development. So up until 6 weeks, the whole skeleton is cartilage. And then, so this is in utero, obviously, the baby hasn't been born yet. By birth, most of that has been replaced, like I said, by bone, but it does continue into your late teens and early 20s. So some of you guys may still be undergoing endochondral ossification and replacing cartilage with bone tissue in very small amounts. So I don't have steps for how this happens. I just kind of have an overall description of what's going on. So what's happening here, you have osteogenic cells. They're entering that cartilage blueprint. So you know osteogenic cells then will become the osteoblasts and then the osteocytes, right? But starts with the osteogenic cells getting into the cartilage. That's kind of the blueprint, and then that's where the bone will be produced. And then that replaces the cartilage. The cartilage basically dissolves away, dies off, and you have bone left. There is still some cartilage, like I mentioned, when the baby is born. So at the joint surfaces, which I mentioned when I talked about long bones, that was the articular cartilage. So you have cartilage where your bones come together to allow for smoother movement. Otherwise, it's pretty much all bone tissue, like I said, other than where we know we have cartilage, like our nose and our ears, for our entire lives. But everything that should have turned into bone has essentially turned into bone by birth, other than some of that, some additional cartilage at the joint surfaces. Oh, and the epiphyseal plate. So the epiphyseal plate is that growth plate. I talked about it some. I'll talk about it a little bit more here in a minute. But that's what allows for the lengthening of bones. Okay, so those are the two types of bone development. Like I said, I know it gets kind of confusing and it's hard to picture, but hopefully that mostly made sense, at least the differences between the two. This diagram, I think, is from your textbook. It goes into a little more detail probably than I went into, but if it's helpful to kind of see an image of what I'm talking about with endochondral ossification specifically, since this is how most of your bones developed in your body. You start here in utero. Basically the blue represents cartilage. So basically the whole skeleton will be cartilage. We're looking at just the knuckle area. You still have cartilage. Eventually capillaries come in and you start to get this bone tissue, which is the brown part. There's still cartilage at the ends. It lengthens and then the cartilage kind of slowly migrates further and further towards the end. So you have less and less cartilage as you grow into adulthood. So here, this brown represents the bone tissue, the blue represents that cartilage tissue remaining. Okay. I'll just barely get into the bone growth and remodeling process, and we'll finish it up on Wednesday. So like I said, your bones basically are growing and remodeling throughout your life. So they're not static once you stop growing. They're still basically dissolving and reforming throughout your entire life. They're growing in two directions. Obviously in length. So when you were 2, your limbs were a lot shorter than they are now. So it definitely grows in length. And also in width. So your bones will thicken over time. And there's basically two different names for growth in length and growth in width. And I'll talk about those in just a second. All right, back to the epiphyseal plate. So I've mentioned this a few times, so you probably want to know what the epiphyseal plate is and what the purpose of it is, what it's made of, all of that stuff. So just a gentle hint there. The epiphyseal plate is really important in bone tissue, in the bone tissue chapter. The epiphyseal plate is where bones add new bone tissue in order to grow in length. It's an area at the ends of your long bones, specifically, of hyaline cartilage. So hyaline cartilage is being replaced by bone over time. So this would be a type of endochondral ossification or osteogenesis. You have cartilage being replaced by bone. So if we look at this x-ray here, this is the lower leg bones, this is the femur, the upper leg. And you can see the epiphyseal plate at the ends of all of these bones. So that is basically a layer of cartilage, and bone is being added on the inside of that plate. So slowly, slowly over time, there'll be more and more bone tissue added, which is going to lengthen that bone. So here, for you guys on Zoom, here's the epiphyseal plate. And bone tissue is basically being added where this, it looks like an opening, but that's just cartilage, where the cartilage is, and it's replacing the cartilage over time. There's still cartilage there, so it can be replaced by bone, obviously, as the bone lengthens. Okay, so epiphyseal plate. That growth from within, so bone elongation. So the lengthening of a bone is called interstitial growth. The thickening of a bone has a different name, which, yeah, should get to on the next slide. So interstitial growth is growth from within. So in that epiphyseal plate, that's growing within the bone. That's interstitial growth, and that leads to bone elongation. So that's my son. And he has tiny little limbs, right? His limbs are super short. Right now, that you can imagine the epiphyseal plate just slowly adding more and more bone tissue to that epiphyseal plate, and his little limbs are slowly getting a little bit longer. So by the time he'll become an adult, he'll just have an epiphyseal line. So it's basically a scar. There's no more bone tissue being added. Otherwise, we would just continue, our limbs would just continue to lengthen forever, right? At some point, it doesn't have to stop, but from an evolutionary standpoint, it stops and we don't grow any longer or taller. So then it becomes epiphyseal line. No more bone tissue is being added. So you don't have any more interstitial growth past, like I said, your late teens, early 20s. Okay, so yeah, when all of the cartilage is consumed and there's no more cartilage being formed, no more bone tissue being formed, then it becomes the epiphyseal line. You can still see it, but it's not active. So then the other type of growth, that widening and thickening, is called appositional growth. So interstitial is lengthwise, appositional is widthwise. This occurs at the bone surface. So it's not within the bone, like in between pieces of the bone. It's actually on the outside of the bone. This is going to continue even after elongation ends. So your bones can continue to thicken even after they stop growing in length. This is specifically done through intramembranous ossification. So that's the other kind of bone growth where cartilage essentially, or connective tissue, is replaced or turns into bone. Interstitial growth would be endochondral ossification. All right. I think that's all we have time for today. So we'll finish this up on Wednesday. We'll be done with bone tissue stuff.